In our last video, we spent some time talking about the dot product of two vectors, which was very useful for finding components of forces oriented in certain directions. Probably even more useful than that is the product we're going to talk about today, which is the cross product. And so without further ado, let's get started. All right, so the cross product is basically a vector that comes as a result of a product operation on A and B. All right, so we're going to start and look at our picture here. So let's call this, now unlike the dot product, which gave us back a scalar, the cross product gives us back a vector. So a C vector is equal to A, so it's an A vector crossed into a B vector. All right, so this is the cross, if you will. It's not multiply. We're not doing multiplication here. And it's not like a dot product operator. It is a different operation altogether. What it symbolizes is if I do this operation and I learn the technique, if I have a vector A and a vector B and the angle theta between them, okay, what will happen is that the C vector that comes out of this, when you do a cross product operation on this, is perpendicular to both A and B. Okay, if you remember back in calculus, they would do an n vector is equal to, n1 vector cross into n2 vector was how you define the equation of a plane. They just needed one vector. Well, those two vectors in the bottom, the n1 and n2, those were laying in the plane, in the surface of the plane, and then all I do is I take a cross product and it will get me a vector that's perpendicular to it. There's only two that can define it. Now, depending on the order that you do, you would get one or the other, but we're going to deal with what we call a right-hand rule on this, where if I can pull this out a little bit, this is the first of the right-hand rules, and this is kind of odd to do on I'm going to pull this out a little bit. Okay, it's kind of, so if you see my right hand, that's kind of like this. I'm going to turn the paper a little bit, and what it is if I do an A cross a B, I can put a right-hand product, so I'm going to put my hand on A on this thing. And so if I do a cross product onto C and I curl my hands towards B and stick my thumb up, that's the direction of C. Okay, now again, I'm drawing on a two-dimensional surface, but that's a right-hand rule for knowing the direction that's going to come out of this. Now do it the other way. If I do B cross A, now I'm doing this, and again, you've got to use your right hand on this. Kind of twist my arm around here, lay it over on B, and then I'm going to curl it towards A. My thumb is now pointed downward into the paper, if you can replicate that. I know it's pretty sloppy to show on a video, but it's kind of a useful trick for being able to understand which vector comes out of both of these. Okay, so A cross B gets me up, and then B cross A gets me down. Okay, and so that's one of the useful things that we're going to play with. All right, let's zoom back in just a little bit so we can see things. Okay, all right, so just like we did before, there is a basic equation. The magnitude of vector C is basically the magnitude of A, okay, multiplied by the magnitude of B, multiplied by the sine of theta. If you remember the dot product, this guy was a cosine on there, okay, and it also had some vector terms, but the magnitude is very, very simple on this. Okay, so the laws of operation is that if I do an A crossed into a B, that is not, notice the not line right there, not the same thing as B cross A. So these are not, I have to be careful of the order that I do these on. And this will be important when we start getting into applying them in statics. Very specific ones have to go first versus second to give you the results that you expect. Okay, but we do know that because of what I just showed you with the right-hand rule on these, that A cross B got me this guy and B cross A got me the guy going down. Well, they're the same magnitude, okay, but one is in the opposite direction of the other. So I can correct A cross B and just do a negative of B cross A instead, like that, okay? And that's kind of what this picture is showing. If I do A crossed into B, right-hand rule gets me theta, my C up, and then B cross A down gets me the one that's acting down, which is a negative C vector, or is B cross A. Okay? All right, so that's what we kind of have happening here. Now, we can multiply by scalars, okay, and just like with the dot product, I can put the scalar on. So if I have a scalar little a, and that's A vector crossed into b vector. I can do little a times the a vector, multiply that through, cross into b, or I can put the scalar on the b term. Okay, so a crossed into little a b. Okay, or I could cross them first and then multiply by the scalar at the end. Doesn't matter. They all give you the same calculation. Okay, for what's going on there, and they will all give you a vector in return. Okay, distributive law, it still works, which is nice. So if I do an a vector crossed into a b plus a d, so these are two resultants, okay, or a resultant of two vectors. So then I could do a cross b plus a cross d. Now this identity is pretty useful, especially since we deal with resultants a lot in forces. That when I start doing cross products on forces, the cross product operator, as you'll see, is a little bit cumbersome. It's not hard, but there's just a lot of algebra and a lot of opportunities for math or sign errors on this. Okay, and if I have to do it twice, that's a little cumbersome. Whereas, so two cross product operations versus just one, this is a very cool simplification trick that you can kind of take a look at. We'll show you some more when we get to some of the problems later in the series. I'll show you where that's come from, but just kind of file that one away as a cool trick to remember. Okay, all right. The Cartesian vector formulation, as you do the operations, anytime I have an I crossed into a J, it gets me a K. Now, unfortunately, the only ones that will zero out are I cross I is 0, J cross J is 0, and K cross K is 0. Okay, all the others give you a different vector, but you'll notice that if I have an I and a J being crossed together, it gets me a K. Okay, whereas if I have a J crossed into an I, it gets me a negative K. Well, there's that negative sign thing that we talked about. J cross K gets me I. So again, one in the I direction, one in the J direction will give me one that's perpendicular to both, has to be the K. And so this is the identity for remembering those. But you got to be careful with the minus signs that are on this. So what I do is I like to draw these, I draw a little diagram to kind of remind me of this. Okay, and so what we do is I put an I at the top, a J at the bottom, and a K here. Okay, and if I go counterclockwise on this, I cross J gets me positive K. Okay, and so what we're defining is counterclockwise is positive and clockwise is negative on this circle. You just got to remember to put everything in I, J, K in that order. And so if I do J crossed into I, gets me a negative K if I go this direction. So I like that little image to kind of remember that one. Okay, so but all that it's doing is basically telling you what is here. You can memorize these if you want. I just graphically, my brain just works better that way. So anyway, whatever works for you is fine. So all right, so that's our basic operations. All right, so now the question becomes, well, what do you do with it? All right, and so here's my A cross B. So that we know is going to get me a C vector. Well, the resolution of this is a 3×3 determinant. Okay, now for A vector and B vector, we're going to define those as we have previously, that A is some AX component I, AY component J, a Z component K, all added together. So that's a vector in the I, J, and K directions, or X, Y, and Z. Okay, and then B is the same thing, BX, BY, BZ with I, J, and K. No problems. You've seen this, several times already before. So if I do this, the way that you evaluate this cross product is I take the determinant and I do I, J, K, and then I can do, on the first line, I put the first vector. So I'm going to put the components AX, AY, AZ of that vector, and they go under those columns. And then B is BX, BY, BZ. Okay, now, once you have a determinant, now we can go back and we can do our algebra skills for determinants and matrices and all those kind of operations. Okay, but what it basically boils down to is that I can take an I multiplied by a subdeterminant here. All right, so we'll go ahead and, in fact, we'll jot this one out just so we can see it. So I can say that A cross B, pull that down a little bit, A cross B is going to be equal to then I of AY, AZ, BY, BZ, okay, is the first term, minus J, and that will be AX, AZ, BX, BZ, okay, plus K, which will be AX, AY, and BX, BY. It will be the vector that comes out of all this, okay? So that would be the operation. So you can see it's like I say, it's not a hard operation, but it's just lengthy. And then I have a 2 by 2 determinant, which remember is ay times bz minus az times bx, all that multiplied by I. Okay, and then each of these. Now the thing to make note of is the minus sign that's right there. Okay, there is a sign flip on this as you try to work this thing out. So minus j ax, so then it would be a minus j times ax bz az bx, and so forth and so on. And you can do the algebra to carry that out. If I go through all of that and I don't make any mistakes along the way, I get a nice friendly equation that looks something kind of like this. Okay, so you can remember this, and all this is, if you look, this is the I, and there's that determinant, that 2 by 2, ay times bz, right? Oops, pull this down a little bit. ay times bz minus az by. That's the terms that's inside of here, multiplied by I. And then I could do ax bz az bx. Okay, and so there's a minus ax bz minus az bx multiplied by j. So there's a minus running here, so you got to watch that one. And then the same thing for the k. It's exactly where it's coming from, is this 2 by 2 resolution, if you will. All right, now I'm going to show you one other method that isn't on these notes, but I'm going to go ahead and kind of pencil our way in a little bit. Something called Sarrus Rule. Okay, which if you don't like doing it that way and keeping track of all the signs, I actually prefer to do it this way. Okay, where again, we're playing with the vector that's happening here. Okay, so let's just rewrite this real quick. I, j, k, and then do ax, ay, az, and bx, by, bz. All right, and then I'm doing a determinant on this guy. The way that you do Sarrus's rule is I basically augment this and rewrite I and j outside of it. And so this becomes ax, ay, bx, and by. Okay, and there are two steps. The first step on this is I take everything from upper left to lower right, and I circle them on the diagonals. So you can see that's why I had to add 2 rows, is to be able to help out the z guy. You could also say that it wraps around, but I just prefer to augment it this way. And so I can take I times ay times bz, and j times az times bx, and k times ax times by. Okay, that's the number 1 calculation. Okay, and we're going to do, so that's, upper left to the lower right will get me that one. Okay, I'm going to do the same thing now in the other direction, and we're going to call that as calculation 2. So now I'm going to take and do this. And I can write it this way. Everything inside of those, wow, those are really straight lines, weren't they? Okay, but anyway, everything inside of that set of circles I call as number 2. All right. So again, you don't have to worry about signs. There's no positive negatives. I mean, the magnitudes may have, the components may have a positive negative sign when you do the operations, but as far as keeping track of this artificial one that we had to add back up here, I don't have to worry about that anymore. So this is going to be lower left to upper right on there. Okay, and then what we've done is then A crossed into B, which is my C vector, is simply number 1 minus number 2. Okay, and so that's kind of what we have happening here. Okay, and so that's all there is to it. That's Sarrus's rule. Very, very handy, very, very convenient for working with these vector operations. So it's a very, now, like I say, it's cumbersome to do this, but it makes dealing with 3-dimensional vectors so much more convenient. We're going to get into a topic known as moments, probably in the next video, starting up with that, in which it's a rotational effect caused by forces. Well, that calculation is actually an operation, is a cross-product operation between the force and a position vector. So if I can get these things set up, I can now handle 3-dimensional calculations very, very easily on those. All right, the thing that's kind of interesting in all this is that this is C. Well, if we define C vector as being Cx times I plus Cy times J plus Cz times K, well, just like before, this is a resultant of, maybe this guy we call as a Cx vector plus, and this guy here is a Cy vector, and then plus this guy here is a Cz vector. That's all that we're doing. And so then this is, well, vector addition. These are all vectors. I'm adding together. This is a resultant on this thing. All right, so that's a resultant. on there. So kind of some cool things that you can do just with the basic vector stuff that we have. And so just understanding what's happening. And so this is the stuff that's acting in the x direction. This is the stuff in the y, and this is the stuff in the z. I can always bounce back and forth with these Cartesian vectors and find the components of things just by doing, even though I was doing an operation that may or may not have been, you know, in a Cartesian plane, I can still break it down into its components in those directions based off of this idea of being able to do, whether you choose to do the determinant method or do Sarrus's rule, it doesn't matter. It's very, very handy and very, very cool. So anyway, we'll go ahead and we'll stop there. We'll put these things to use in our next lesson, okay, which will be when we start talking about moments of forces, but that's a preview for next time, so stay tuned. As always, if you found this helpful, toss us a like or subscribe, and of course, if you've got any questions, leave us some feedback down below, and I will get right back with you. Otherwise, have a great afternoon, and we'll see you all next time. Happy engineering.